I'm Traxie Lopez from Bay 30 and I hope you're having a great day. Linear programming sensitivity analysis has been introduced to us previously, so now we are going to continue with the given problem with the Beaver Creek Company. Remember that the objective of sensitivity analysis is to determine the range of values for a specific objective function coefficient over which the solution point remains optimal. A little recap. So what we have here is a graph showing the optimal solution, which is point B. This is a graph from the Beaver Creek Company example. Moving on, changing the function x sub 1 coefficient, wherein increasing the profit for a bowl from $40 to $100 makes the objective function line steeper, so much that the optimal solution point changes from point B to C. Alternatively, increasing the profit for a mug from $50 to $100, the objective function line would become flatter, to the extent that point A would become optimal with x sub 1 is equals to 0, x sub 2 is equals to 20, and z is equals to $2,000. The coefficient of x sub 1 in the objective function is originally $40, but at some value greater than $40, point C will become optimal, and at some value less than $40, point A will become optimal. The focus of sensitivity analysis is to determine those two values, which we will refer to as sensitivity range, wherein x sub 1 is equals to c sub 1. For our example, we can look at the graphs and determine the sensitivity range for the x sub 1 coefficient. The slope of the objective function is currently determined as follows. Z is equals to 40x sub 1 plus 50x sub 2, and 50x sub 2 is equals to z minus 40x sub 1, to x sub 2 is equals to z over 50 minus 4x sub 1 over 5. Side note, slope of an objective function line c sub 1 x sub 1 plus c sub 2 x sub 2 could be equal to negative c sub 1 over c sub 2, wherein slope of a constraint a sub 1 x sub 1 plus a sub 2 x sub 2 is equals to b to negative a sub 1 over a sub 2. If the slope of the objective function increases to negative 4 over 3, the objective function line becomes exactly parallel to the constraint line, wherein 4x sub 1 plus 3x sub 2 is equals to 120, so negative c sub 1 over 50 is equals to negative 4 over 3. Then cross-multiplied to negative 3 c sub 1 is equals to negative 200, divide negative 3 on both sides, we will get c sub 1 is equals to $66.67. Now we have determined that the upper limit of the sensitivity range for c sub 1, the x sub 1 coefficient, is $66.67. If profit for a bowl increases to exactly $66.67, the solution points will be both B and C. If the profit for a bowl is more than $66.67, point C will be the optimal solution point. Now the lower limit for the sensitivity range can be determined by observing figure 3.4b. In this case, if the objective function line slope decreases or becomes flatter from the same slope as the constraint line x sub 1 plus 2x sub 2 is equals to 40, then point A becomes optimal along with B, wherein the slope of this constraint line is negative 1 over 2. In order to have an objective function slope of the profit for a bowl would have to decrease to $25 as follows. Negative c sub 1 over 50 is equals to negative 1 over 2, to negative 2 c sub 1 is equals to negative 50, wherein c sub 1 is equals to $25. This is the lower limit of the sensitivity range for the coefficient. So now the complete sensitivity range for the coefficient can be expressed as c sub 1 is less than or equals to 66.67 but greater than or equal to 25. This means that the profit for a bowl can vary anywhere between $25 and $66.67, and the optimal solution point x sub 1 is equals to 24 and x sub 2 is equals to 8 will not change. Of course, the total profit or z value will change depending on whatever value c sub 1 actually is. For the manager, this is useful information. Changing the production schedule in terms of how many items are produced can have a number of ramifications in an operation. However, with the preceding sensitivity range, the manager knows how much the profit, and hence the selling price and costs, can be altered without resulting in a change in production. So what we have here is a sensitivity ranges for the objective function coefficients for our example. Notice that this output provides the upper and lower limits of the sensitivity ranges for both variables x sub 1 and x sub 2. So since sensitivity analysis is a very long topic, I will just briefly introduce sensitivity analysis of right-hand side values of constraints, where I'm going to define two terms. The first term is slug. Slug is the difference between right-hand side value and left-hand side value. It is the amount of resource that is not used. The second term is surplus. Surplus is the difference between left-hand side value and right-hand side value of constraint. It is the amount by which consumption exceeds the minimum requirement. So a constraint would have either slug or surplus depending on its side, and it is called binding, wherein left-hand side is equals to right-hand side. For much more detailed explanation, open page 102 of the book or the PDF, and the following links might help too.